Hey guys, so recently I've been hearing a lot of hubba bubba about this guy named Isaac Newton, who was apparently really famous in the science world. He was born in like the 17th century, which is like 1600 or something, so really long ago. Apparently he made like these laws that are super duper important today, and since they're law, like they can never be wrong, like they're always right. And I really love a person with conviction, so I just need to know more about it. So yeah, I'm gonna take you on a trip with me today as I learn more about Newton's three laws of motion, potion, locomotion, commotion, motion. Newton's three laws of motion. Get excited. Okay, so we're in school now, and I'm gonna try and find anyone who knows about Newton's three laws to help us out. The first law that we're gonna look into is the first law of motion, and I'm gonna go to my AP Physics classroom to see who can help me. So I'm in physics now, and I found a friend, Tamesh, who's gonna help me explain Newton's first law. So, Tamesh, what's Newton's first law?
Newton's first law is an object that's at rest will remain at rest, and an object in motion will maintain a constant velocity unless enacted upon by a net force.
Wow, that's so exciting. Can you give me an example of it?
Yeah, sure. Okay, so like basically a car like braking and then like jerking forward, or a book like moving until it's like pushed. Yeah.
Very interesting. Thank you, Tamesh, for teaching me this.
No worries.
Now I'm on a mission to demonstrate the examples that Tamesh gave to us. Unfortunately, I don't have any friends who are willing to break check themselves in the name of physics, so I will be doing the book example. Okay, so here is a real life example of Newton's first law at work. Right here, I have a book. The book is at rest. And according to Newton's first law, this book will not move until a net force is applied to it. So let's watch it to see if it moves. It has not moved. Now, let's try applying a net force to it. Did you see that? I pushed the book, applied a net force, and the book moved. It moved from position A to position B. And that's because of physics. No, but actually, Newton's first law, an object at rest will remain at rest, and an object in motion will maintain constant velocity unless acted upon by a net force, tells us that since this object had a net force applied to it, it was able to move and gain an acceleration, which would give it a constant velocity. But yeah, physics. After that really captivating book example, I'm now going to show you Newton's first law of motion using word problems. So the problem that we're looking at for Newton's first law of motion reads, what net force is required to keep a 100 kilogram object moving with a constant velocity of 10 meters per second? So knowing that Newton's first law states that an object in motion tends to stay in motion unless if acted upon by a net force, this shows us that if friction is not present, there is no net force required to keep the object moving if it's in motion. And in this scenario, friction is negligible. Net force is only required to change an object's motion. The 100 kilogram object is moving at a constant velocity, so there is no net force acting on the object. Hence, the net force is equal to 0 newtons.
3, 2, 1.
Physics is fun!
So now we're doing Isaac Newton fun facts. Fun fact number 1, he was born on Christmas. Fun fact number 2, he was born severely premature. Fun fact number 3, when he was born, he could fit inside of a coffee mug. Fun fact number 4, his mother left him as a child. Fun fact number 5, she eventually remarried and came back, but because of that, Isaac harbored a very big hatred towards her and his stepfather. Fun fact number 6, he had such a hatred for them that he threatened to burn down their house while they were still inside of it. Fun fact number 7, he died a bachelor and he was actually very stingy with his wealth. So yeah, good to know. The more you know. Okay, so I found someone who I think can help me with figuring out what Newton's second law of motion is. So I'm here with Darlene, and say hi.
Hi.
Can you tell me what Newton's second law is?
The acceleration of an object is directly proportional to the net force exerted on an object and indirectly proportional to the mass of the object.
Wow, big words. Proportions? That's a lot for my brain to
I
handle.
can spell it, Mr. Hugh.
Can you give me an example of that to like help me visualize?
An example would be pushing a desk versus pushing a desk with somebody in it.
Wow, I think I might just go try that. Let's go on a trip. After that exhilarating definition, I'm on a mission now to represent the example given to us. I found a desk with a person to push. Let's get into it.
I'm at about noon. That's not too bad. 2 hours.
Versus.
Thank you. What does that have to do with physics?
You jumped in the back.
You think this is enough?
Yeah.
No, I think we should keep going because these weren't horrible pushes. You have to do it like swift. Yeah, like that. Yeah, like that. Okay, you're done.
All right.
It is evident in this scenario that the desk with the greater mass has a lesser acceleration than the desk with the smaller mass, and this shows the inverse proportionality between acceleration and mass, and it also shows the direct proportionality between force and mass. As the mass of the desk got greater, the force needed to move the desk also increased. Now it's time for me to represent Newton's second law of motion using word problems. So exciting, guys.
Everything else. Got it?
In our last set of problems for Newton's second law of motion, we have an object with a mass of 2.0 kilograms has a force of 4.0 newtons applied to it.
I floss all
What
the
is
time.
the
I have a
resulting
flossing problem.
acceleration? So here we have 2.0 kilograms, 4.0 newtons of force, and what is the acceleration? So for this, we're going to be using the equation A equals F over M, which shows us that acceleration is directly proportional to the force applied to an object and indirectly proportional to the mass of the object, very similar to the definition that was given to us by Darine. Now, we're going to substitute in, so F over M, that equals 4.0 newtons over 2.0 kilograms, which gives us 2.0 newtons over kilograms, which simplifies to 2.0 meters per second squared. I hope you can see that. But yeah, our ultimate answer is the resulting acceleration is 2.0 meters per second squared.
Wow! Physics is fun!
Go.
Biology is the best.
Physics is fun.
No.
After learning about the first and second laws of motion, it's now time for us to find out about the fourth. Okay, so after my quest on finding out what Newton's second law of motion is, I now have to figure out Newton's third law of motion. And I brought my friend Richie Rojas here. Okay, so I was looking for someone else to teach me about Newton's third law of motion, and I found this really nice guy named Richie, but he didn't want to be recorded. So we're back with Darine, our resident expert. Darine, can you tell me what Newton's third law of motion is?
When one object exerts a force on another, the second object exerts a force on the first that is equal in magnitude and opposite in direction.
Oh wow, that's so amazing. Can you give me an example of it? Because I'm a little confused.
Pushing someone and being pushed back.
Interesting. I think I'm gonna go try that. You guys already know the deal. We're representing this law with an example. Unfortunately, we will not be using the example Darine gave to us due to lack of supplies. For our first example, for Newton's third law of motion, we have an elastic band, in this case a scrunchie. You're gonna place it on your wrist and you're gonna stretch the scrunchie and release it. As you can see that when you exert the force of stretching the elastic band, it reacts by hitting you back once you release it. So for the action, there's a reaction. And it's equal in magnitude, which is seen by if you pull harder, it hits you harder. And it's opposite direction. Obviously, I'm pulling to the left and I'm pulling to the right and it's hitting me to the left. Physics is painful. It's time to find another available whiteboard to do our next word problem. Yay! So, as seen in Newton's third laws, there are action and reaction pairs. And I'm going to represent symbols to you in some of my examples. So the first example I have is a car going down the road. As the car moves forward, it pushes backwards on the road. So this is the car, and this is the road. And the car is pushing backwards. But this act of pushing backwards on the road, there is the equal and opposite reaction from the road, and in turn, the road pushes the car forward. So, as the car pushes backwards, the road pushes it forward. For our second example, we have a rocket ship. Now, the rocket ship is moving forward because the gas that is expelled from the background here, right here, is being pushed backwards. So as the rocket moves forward, there's an equal and opposite reaction in which the gas is pushing backwards. So rocket forward, gas backwards. Let's label that. Rocket.
Physics is fun.
Okay, breaking news, guys. I just found the Isaac Newton real in the flesh, and Mother Nature is about to harm him. This is crazy. Let me show you.
Oh my gravity!
Hey guys, so I'm back at home. It's been a really long day. I had so much fun learning about Newton's 3 laws of motion today. I've learned so much from all my really smart colleagues and peers. So just as an overview, just so that we can go over what we've learned today, Newton's first law of motion is known as the law of inertia, and it states that an object at rest will remain at rest and an object in motion will maintain a constant velocity unless acted upon by a net force. Newton's second law of motion states that the acceleration of an object is directly proportional to the net force exerted on the object and inversely proportional to the mass of the object. And Newton's third law of motion, the action and reaction law, states that when one object exerts a force on another, the second object exerts a force on the first that is equal in magnitude and opposite in direction. So these are great bits of information to know for your everyday life. I'm so happy I've been fueled with knowledge of physics, and it's been a really great experience. I hope you guys enjoyed coming on this day in the life with me, and I'm hoping that I could see you soon. You know, maybe next time we could do another physics concept, like, I don't know, gravity. That's a joke. Anyways, this is so great, guys. Thank you so much, and enjoy some bloopers. Now we're gonna do some Isaac Newton fun facts.
I just scream out. Can I hop into the middle at the end and be like, this is fun?
Girl, it's already recording, bro. You know what? Take 2. Stop.
Hey, Mr. Key,
Hi.
try to bail her.
Richie, come back. You should be in the video. Richie, I'm gonna get you next period.
Wow, this is fun.